Okay, this is a continuation of the video on calorimetry because I accidentally stopped recording and could not resume. So you will see when you see the lab for this week, a calorimetry lab. And in a calorimetry lab, you use a device called a calorimeter. A calorimeter is a device that measures the flow of heat. And what we use in the lab for a calorimeter, and what you'll see me using, is styrofoam cups, because styrofoam cups are good insulators of heat. There are other fancier calorimeters. And if you'll recall, at the beginning of Chapter 5, we talked about different types of systems, like an open system that exchanges matter and energy with the surroundings, and then a closed system that would only exchange energy with the surroundings. The calorimeter that we'll be using is an open system, okay, because it is a coffee cup, a styrofoam cup. You'll see I'll try to put a cover on it, but clearly if there were steam associated with it, it would be able to escape. There's a different type of system when you use a closed system. Y'all will recall that an open system also means that it's a constant pressure system. And we talked about constant pressure earlier. If you were using a closed system calorimeter, which is not what we will do in lab, but you may see problems like this on Connect, a closed system is constant volume. So the volume doesn't change. So that means in a closed system, if you're burning something in a closed system, if you have, it usually takes a metal, it's lined with styrofoam, and it's metal, and it has a really tight lid on it, a closed system. And so you might burn something in the closed system. As it heats up in there, you guys see it's constant volume, so the pressure can really build up in there. Closed systems a lot of times are called a bomb calorimeter, okay, because the pressure will build up inside that calorimeter as the heat increases. That bomb calorimeters are what's used to do the calorie content in food, okay? Now, let's look at a problem using an open system calorimeter, and this problem will get you kind of ready for what you guys are going to be doing in lab and the calculations you're going to be doing. So when you get ready to finish the lab, you can reference this problem. Okay, so you might want to take a moment and pause the video and write that part down. And when you get it written down, I want you to think about this before you continue playing the video. You have a piece of metal. 16.984 grams is how much the metal weighs, okay? In this problem, you do not know what the metal is. You don't know if it's aluminum or gold or copper or what. But you've heated it up to 100 degrees Celsius, which actually you could hold that in your hand because metals have small specific heat. So it doesn't take a whole lot of heat for a piece of metal to get to 100 degrees Celsius. Now, you could not hold, if it was water at 100 degrees Celsius, it'd be boiling. You wouldn't want that on you because there's a whole lot more heat in it. Okay, so that's just me trying to drive home what the Q and the S. So you take this piece of metal, it's warm, and you put it in water, in 30 mils of water, and this water is at 25 degrees Celsius, okay? So that's room temperature. So what's going to happen to temperatures and heat here? Think about it. The temperature of the metal is going to start to drop. And the temperature of the water is going to increase because the metal is going to give its heat, Q, to the water. What kind of temperature change do you think the water is going to have? Come up with a number. Is it going to go up to 26, 28, 35, 54? I mean, what do you think? And you'll see this in lab. Guys, water has a high specific heat. So even though the metal it doesn't take a whole lot of heat for the metal to go up to 100 degrees Celsius. when it transfers the heat to water, the water temperature is not going to go up that much. Maybe 3 degrees, 4 degrees, sometimes 2 degrees. It just depends on what the metal is. So let's continue with this problem. The temperature of the water and the metal, they're going to come to the same temperature. So we're going to say they equilibrate at 27.2 degrees Celsius. Let's calculate the specific heat of the metal. So, what we have here, in a sense, is two different systems we're looking at. We've got the metal, and we've got the water. And it's a calorimetry problem, and so we know the formula for calorimetry is Q, M, S, and delta T. I'm going to break that down to final temperature and initial temperature. And before you go through and watch me do it, I would like for you to pause the video and you take the numbers in the problem and put them in this table where they belong. And then I'll do it with you. Okay, the mass of the metal is 16.984 grams. I'm just reading the problem, and when I come to a number, I'm assigning where it goes. 100 degrees Celsius is the initial temperature of the metal. 30 milliliters of water is a volume, but I know the density of water is 1 gram per mil, so I know that's 30 grams of water. And the initial temperature of the water is 25 degrees Celsius. The water and the metal equilibrate, so their final temperature of both is 27.2 degrees Celsius. And we're asked to calculate the specific heat of the metal. Okay, that's a question mark. So that's what we're looking for. We don't know the identity of the metal, so we can't look up the specific heat in the table. But we do know that we're dealing with water, so we could look up in the book, page 200, is that what it, yeah, there's a table of specific heats, and the specific heat of water is 4.184 joules per gram times degrees Celsius. And so if that's the specific heat, I've got to watch and make sure all my other units match that. So my mass should be in grams, and it is, and my temperature should be in Celsius, and it is. And so the first thing I'm going to do is I'm going to calculate the delta T. 27.2 minus 25 is 2.2 degrees Celsius. And then I'm going to toggle between two slides as I can calculate Q. So Q for the water is equal to the mass of the water times the specific heat of the water times the change in temperature of the water. The mass of the water is 30 grams. The specific heat of the water is 4.184 joules per gram times degrees Celsius. And the delta T of the water is 2.2 degrees Celsius. So the Q for the water is 276.1 joules. Okay, I'm not worried about sig figs right now because I'm not finished with the problem. 276.1 joules. So I'm going to go over that here and record that's 276.1 joules. That's how much heat the water had to absorb in order for its temperature to go up. Where did it get the heat from? It got the heat from the metal. So the first law of thermodynamics says that the heat absorbed by the water, this is positive because it came out to a positive number in our calculation, because the metal released that much heat. So the Q for the metal is negative 276.1 joules. So now we can solve for the specific heat of the metal. First, let's double check the delta T. Final minus initial. 27.2 minus 100 is, the delta T is negative 72.8 degrees Celsius because it's the final minus initial. And so now I can rearrange Q equals MS delta T using my algebra. S is equal to Q divided by M delta T. And so this is all about the metal. I'm going to put a little M here to remind everyone. These are metal numbers. The Q of the metal is negative 276.1 joules. The mass of the metal is 16.984 grams. And the delta T for the metal is negative 72.8 degrees Celsius. So we're going to punch that in our handy dandy calculator. And y'all, I get 0.223 joules per gram times degrees Celsius. It's positive because if Q is negative and the delta T is negative, the specific heat's a positive number. Guys, specific heats are always positive numbers. Okay? And remember, as I told you, for metals, the specific heats are small numbers. This is a small number for specific heat. It's a decimal number. Okay? And there's more problems like that in your book on some of those pages, 200 through 205, where it does calorimetry. Now, I want to go ahead and list some end of chapter 5 problems that you guys can practice working. This will help you prepare for the test. I know you also have Connect. So, end of chapter 5. These begin on page 220. Everything I'm giving you has the answers in the back of the book. They are numbers 7, 13, 15, 25, 27, 35, 37, 40, I got that out of order, 47, 49, 51, 63, 67, and that's it. And that wraps up chapter 5. Your next lectures will be on chapter 6.